his work when he started doing other things with Catarina Lobo and Mathilde Josac, who gave us a lot of very nice data. You will see what kind of data later. So what's interesting about cluster galaxies? Well, it's that they are undergoing a lot of environmental effects, mainly two types of effects: gravitational effects that affect both stars and gas, and that I'm not going to talk about very much today. And then dynamical effects that affect only galaxy gas through ram pressure stripping, where the hot intracluster gas interacts with the gas of infalling galaxies. And so this can lead to several effects that can be combined, but that are not all present at the same time, sometimes, depends. So you can have compression along the leading edge of the disk, and then you really see that the disk has an edge, which is not always seen in galaxies. There can be an increase in star formation during the peak stripping phase, when the stripping is maximum. And then, of course, when all the gas is used to make stars, there is quenching of star formation. There can be the formation of tails of gas in the wake of the galaxy, because the galaxy is moving, usually at rather high speed, not necessarily, but sometimes. There can be condensation of knots, star-forming knots in the tails, and this can lead also to asymmetric morphologies. So jellyfish galaxies, from what I found, were first named like that by Becky, who made hydrodynamical simulations and found some galaxies that looked pretty much like the two that I'm showing, which are very typical of jellyfish galaxies, and that's what gave the name, because you have a main structure and then a tail that can be very long. There has been a series of very nice papers by Bianca Poggianti and her team, based on VLT Muse data. So GASP is gas stripping phenomena in galaxies, and since 2016 or 17, there have been I don't know, at least 20 papers published on the topic, and they have extremely nice data. So we're not competing with them, but we're just trying to do something on jellyfish galaxies, and also to prepare a sample that can be used later for more detailed analysis. So what I just wanted to say is that extended tails are seen in ionized gas, but you can also see young stars in broadband filters, and we only have broadband filters, but we are still detecting long tails in some objects. This is one of the typical objects that we found. So we try to look for jellyfish galaxies at relatively high redshifts. And this is one of the examples. They're not all as clear as this one, but we looked for jellyfish galaxies based on HST data in order to have a good spatial resolution in 40 clusters that have Daft-Fada or Clash images, all from HST, and also that have galaxy spectroscopic redshifts, because we only limited our search to galaxies that were confirmed to belong to the clusters and not to have, they're not foreground or background objects. So we want them to belong to the cluster. And then there is one cluster that is max, that I would call max 0717, which is at redshift 0.55, for which we have a large mosaic of HST images in 2 filters. We have over 600 spectroscopic redshifts, and we have a magnitude catalog with optical and infrared magnitudes. So we will be able to derive stellar population properties for the galaxies in this cluster. So how did we select them? Well, we looked at all the galaxies with redshifts within about plus or minus 2 times the velocity dispersion of the cluster. We selected them by eye because it's difficult to do it in another way. And so that's why Simon Chiche did the work first, and then I did the work again without looking at his results. And then I compared both results, and we classified them following a classification that has been proposed by Harald Ebling, which goes from J = 1 for the less probable ones to J = 5 for the most probable ones. And we eliminated galaxies that had obvious gravitational interactions with a neighbor within a projected circle of 50 kiloparsecs, just to get rid of galaxies that had gravitational interactions, because jellyfish galaxies are supposed to be only due to ramp pressure stripping. So for MAX 0717, we have increased the velocity interval, the redshift interval, because plus or minus 2 sigma v was kind of small, since it's a very large structure with probably several merging clusters and a long filament. So finally, we ended up with 81 jellyfish candidates in a redshift range, which is rather large. So in red, you have the redshift histogram for all the galaxies for which we have redshifts. And in green, you have the redshift histogram for the 81 jellyfish candidates. So you can see that they're pretty similar. There doesn't seem to be a great difference between the two histograms, just looking at them. And so this is the distribution that we have. It's 81 jellyfish galaxies. So the yellow rectangle is the full HST mosaic. So you have a scale of 1 megaparsec down there. So you see it's really a huge structure. We find, yes, I forgot, the black circle is 1 megaparsec radius around the cluster center. And you can see that it's really very long. And the green contours are the green contours of the density map based on red sequence galaxies that was drawn in a previous paper. So you can see that there are jellyfish galaxies everywhere. Here, we only plotted the jellyfish galaxies of types 3, 4, and 5. That is the most probable ones. And the blue and red colors just come because correspond to the selections by Simon and the selections that I made. And sometimes they're superimposed, so just to show both. Here are 2 other jellyfish candidates in MAX 0717. You can see that they look pretty different. They can have very different shapes. In the top left, you have you can see one that looks pretty much like the one that I showed you first, sorry. And this one is completely different, but you can see that there's an edge. So in many cases, you have the feeling that you can guess what is the direction of the cluster of the galaxy within the cluster. So what are the properties of these 81 jellyfish galaxies? Well, if you look at the color magnitude diagram on the left, you can see that they are mainly blue galaxies. The color magnitude diagram shows blue points for each jellyfish galaxy. The red line is the red sequence that we had determined previously. And maybe I can even use the laser pointer, yeah. Yes, and the dashed lines show the interval of the red sequence. So plus or minus 0.3 around the red sequence. And you can see that most of the jellyfish galaxies are located below the red sequence. And there are just a few examples, which are, I don't know, probably dusty galaxies up there above the red sequence. Another interesting point is that here on the right, you have the distribution as a function of the histogram of the distribution as a function of distance to the cluster center. So in red, you have all the jellyfish galaxies, and in blue, you have the jellyfish galaxies classified as types 3, 4, or 5. And you can see that they're spread all over the structure, which is already what we saw in this figure. And this shocked very much our referee, because our referee thought that jellyfish galaxies were mostly concentrated not very far from the center. And here we find, in this cluster, we find that they are spread all over. For the other clusters, we have found 97 jellyfish candidates in 22 other clusters, and that is in the redshift range between 0.2 and 0.9. And among those galaxies, there are 31 that have up to 17 measured magnitudes from the clash survey. So here also, for those 31 galaxies, we will be able to make a stellar population synthesis with these magnitudes to derive properties on the star formation rate. And so the fits were made with the software called Le Phare through an interface that is now available in Marseille at LAM, which is called Gaspar. And it's very nice because you just have to make your catalog with the right format and send the catalog, upload the catalog, and then they send you back the results. So we did this for 79 of the jellyfish candidates in MAX 0717, for which we had 8 measured magnitudes. We did this also for 122 non-jellyfish galaxies in the same redshift range, of course, so that is plus or minus 4 sigma, in order to have a comparison between jellyfish and non-jellyfish. And we did it also for the 31 jellyfish candidates in the other clusters, for which we had up to 17 magnitudes. And so we found results. This is just the illustration for 2 jellyfish galaxies of MAX 0717. So the black points are the magnitudes in different filters, and the red lines are the best fit spectra. So in all the 79 jellyfish galaxies, except 2, we have this tiny H-alpha line. And in more than half, we even have not only H-alpha, but we also have H-beta, O3, and O2 lines, emission lines, in the best fit spectrum. So this already shows that they are star-forming galaxies, because you see ionized gas. And these are the main results on the stellar populations. So first, the star formation rate. So for MAX 0717, you see that globally the star formation rate is between -1 and +2 in logarithmic scale. Whereas for non-jellyfish galaxies, the values are spread over a much larger range. And if you see -1 is here and +2 is here. And so you have a whole bunch of galaxies that have a much smaller star formation rate. And for the other clusters, for the 31 galaxies in the other clusters, the range is pretty much the same as in MAX 0717. If we now turn to the specific star formation rate, that is the star formation rate divided by the stellar mass, on all the plots, you have a line here, a dashed line, which is at -11 in logarithmic scale. And this is usually the value that is taken as a limit for star-forming and non-star forming galaxies. So star-forming galaxies are above -11, and you can see that in MAX 0717, as well as in the 31 other galaxies. The specific star formation rate is above this limit. So this says that they're all almost all star forming. Whereas if you look at non-jellyfish galaxies in this sample, you see that most of them are not star forming. So this also shows a large difference between jellyfish and non-jellyfish galaxies. And this also confirms that our jellyfish galaxies are indeed jellyfish galaxies and not just jellyfish candidates, as the referee insisted that we would call them. So throughout the paper, we always call them jellyfish candidates, but we really believe that most of them are real jellyfish objects. Then if we look at the age of the stellar populations, well, we can see that in Maxo 717, the age is usually below, well, in majority, below 1.5 10 to the 9th gigayears, whereas for non-jellyfish, the spread is much larger. And surprisingly, in the other clusters, the spread is much larger too. So it seems that the jellyfish galaxies in Maxo 717 are notably younger, maybe because this cluster is undergoing a number of mergers, and this also has recently triggered star formation, so that's why the jellyfish galaxies look younger. And finally, if we look at the stellar masses, they are not very high. You can see that jellyfish galaxies have masses between 9 and 11 in logarithmic units, whereas, not units, but range. And it's more or less the same in the other galaxies, whereas for non-jellyfish, most of the galaxies have masses above 10 to the 10th solar masses. So this has also been found by other people. It seems that jellyfish galaxies are in majority rather low mass galaxies. If we look at the star formation rate as a function of stellar mass, this is a pretty popular diagram. The Peng relation based on SDSS data from 2010 is plotted in green with the, I would say, error bar in green dashed lines. And you can see that the jellyfish galaxies NMAXO 717, the green points are in majority above this line, though there are a few below the line, but most of them are really above the Peng relation, whereas non-jellyfish, which have always been plotted in magenta, half of them are above the line and half of them are below the line. So in general, the jellyfish galaxies in Maxo 717 also show that they are above this relation. In black is the Vulcani relation, which is more or less the same as the Peng relation, but at going up to a somewhat higher redshift. Peng is at redshift almost 0. And for the other clusters, the plot to the right shows that the jellyfish are above the Peng relation, but there is maybe a larger number of galaxies that are below this relation. So this is the plot that I was talking about that Gary is going to like, because in fact, when I put my paper on archive, I got comments from Andrea Biviano a day or two later, so that shows that he really follows the archive much better than I do, because I'm usually a month or two back. But he told me that I should make this kind of plot to compare it with the Mahajan, Memon, and Reshodori 2011 figure 10. So on the right, I show this figure 10, where they plotted in green virial galaxies, in blue infall galaxies. That is, the blue lines are a bit difficult to distinguish from the black lines, but they're here. And in black, what they call backsplash galaxies, so infall galaxies are galaxies that are falling into the cluster for the first time, so crossing the cluster for the first time. And backsplash galaxies are galaxies that have already crossed the cluster and are coming back. And so these backsplash galaxies are limited by these black lines here. And so our jellyfish galaxies in Maxo 717 are distributed here. So this plot, I forgot to say, shows in x-axis, it's the distance projected, of course, distance to the cluster center in units of R200. On the right figure, it's virial radius. That's not very different. for us it was, we calculated the R200 for all the galaxies. In case someone doesn't know, the R200 is the radius within which the average density is 200 times the average density of the universe at that redshift. And here along the y-axis, you have a quantity which is delta V on the line of sight. That is the difference on the line of sight between the galaxy velocity and the mean cluster velocity, divided by the velocity dispersion of the cluster. So these two figures should be comparable. And the lines that Andrea, I sent this plot to Andrea, and he drew the backsplash and infall lines. Unfortunately, he didn't choose the right colors. So the colors are the opposite compared to the figure on the right. So here you have infall galaxies in black, I mean the infall region, and the backsplash galaxies in blue. But you can see that in MAX 0717, it's more or less half of the galaxies are backsplash galaxies, half are infall galaxies, and just less than 10 galaxies are above this limit, the two limits. So maybe Gary will tell me a little more about the interpretation of this, because I'm not really familiar with this. So to summarize our results, the jellyfish candidates have a rather high star formation rate and specific star formation rate. If we compute the average star formation rate, it is 3 times higher than for non-jellyfish galaxies, that is for MAX 0717. Then globally, they have stellar masses between 10 to the 9th and 10 to the 11th solar masses, and they have ages that are mainly below 1.5, 10 to the 9th years. So they are relatively young stellar populations. What I just wanted to point out is that it's difficult to identify jellyfish galaxies. We had to look at them several times and to decide which ones we would keep and which ones we would not. So as I showed, they're young and star forming. As I showed, and I hope to do this in more detail later, they give informations on the cluster dynamics. And we are now presently starting the study of another cluster, which has lots of data that are comparable to MAX 0717. Thanks also to Mathilde Josac, who sent us these data, and it's also going to be part of the internship, the Masters 1 internship of Lucie de Gott, who should arrive in May. Finally, I finished on jellyfish galaxies, but I wanted to answer a question by Valérie, who made the question to Aline 2 weeks ago, and we didn't have the right answer. She asked how the Comedy relation on brightest cluster galaxies compared with normal elliptical galaxies. And so Aline made the plot. So this is the previous plot that Aline showed 2 weeks ago. So the Comedy relation, I remind you for those who were not here 2 weeks ago, is the average surface brightness of a galaxy as a function of effective radius. And the plots, this plot is shown with different symbols depending on the brightest cluster galaxy redshifts. So the nearest ones are in pink and the most distant ones are in blue. And so what Aline had said was that the Comedy relation, which is plotted as a full line, is also detected in brightest cluster galaxies. The Comedy relation is a very old relation that was shown by Comedy, I think in 1977, maybe I'm wrong, but, and on normal ellipticals, and you can see that it's pretty similar, and the dashed line is the Comedy relation for normal ellipticals, and the full line is the Comedy relation for RBCGs. Now, for the Bayet, I'm sorry, I should have read this. the full line is, we didn't really make a fit for our BCGs because as we see, the fit varies with redshift, but the sample of BCGs that didn't go as far in redshift from Bayetal, they plotted this black line. So you can see that they're not extremely different. Okay, I think that's all. If I have, I still have a few minutes, so I'm just going to say briefly something else about galaxy asymmetries in clusters, but that's really work in progress, so it's just 2 minutes. This is work that has been done, that is being done in collaboration with Hector Bravo and his team in Mexico, and it's based on near-infrared imaging and also on neutral hydrogen VLA data. So we are presently writing a paper to present all the VLA data, which is old data, but hasn't been, we haven't been able to finish the work. And so it's based on several clusters, in particular for Abell 85. There were 10 galaxies found to have strong asymmetries. And so now we're going to look at them as if to see if they are jellyfish galaxies or just asymmetric galaxies. And this is based on an asymmetry index that was developed by Yoga Venkatapati. And among them, three were considered as jellyfish. But now that I've done all this work on jellyfish, I want to come back to all these 41 asymmetric galaxies to see if there are more. Yoga did his thesis in Mexico and defended it, I think, a year or two ago. And he developed an asymmetric asymmetry index, which is quite powerful. We also found asymmetries in other clusters. And so that by asymmetry, this is what we mean. Here you have two galaxies in Abell 1367. And so this is what the galaxy looks like. And if you subtract a model, you end up with zones here that are completely asymmetric. And the same for this one, though it's not as clear. So yes, his PhD was in 2020. So this will maybe be a journal club in, I don't know, 6 months from now. Okay, that's all. Thank you.
Merci beaucoup, Florence. Merci. On va prendre quelques questions. Pas de questions? You can, you can unmute yourself. So let's take Valerie. Can you please put on your micro? You can do it yourself, actually.
No, she doesn't seem to be able to do it herself.
But I gave them the ask from you.
I think it's, yeah.
Okay.
Very much, Florence, for this nice talk. So I have two questions. I have the impression of this cluster you showed with about 80 jellyfish galaxies. It's very different from the other clusters that seem to have more like 2, right? You said 90 for 22, 5 for 22 clusters. So I guess you had some indications a priori that you would find many of them in this cluster?
Not really. What I would say is the other way around, is that our redshift, we only looked for jellyfish galaxies for which we had redshift. And this is, of course, completely biased because we don't have the same number of redshifts in each cluster. So we can't make statistics and say this cluster has, I don't know, 20 redshifts and there's only 1, and this cluster has 20 redshifts and there are 5. So it's significantly larger because we don't know the completeness of the redshift surveys. It's for this cluster, Maxo 717, it's the only one for which we have a redshift sample that is really reliable. So for the others, it's just trying to get samples of more jellyfish galaxies, but we can't really say, because some clusters have 20 or 30 redshifts and some have only 2 or 3. So of course, the probability of finding, as I said, we started with 40 clusters And we ended up with 22 clusters, plus I think plus Maxo 717. So there were 13 clusters for which there was a small number of redshifts. And for those galaxies, there was no jellyfish. But that doesn't mean that there's no jellyfish in those clusters. It's just that we don't have enough redshifts. And because we looked at clusters in a relatively high redshift range, we don't have SDSS redshifts, for example. So we would need to make redshift observations to get more jellyfish galaxies in those clusters.
Okay, and I have another question. What are specifically the morphological features that you use to determine? Is it to have an extended tail at low surface brightness? And the other side of the question is, did you take nearby jellyfish galaxies like those you just showed and redshift them to the redshifts of your cluster to see how they would look?
So the second question, no, we didn't do that. I think it's a very good idea, but it's a completely different work. We didn't do it, but yes, it would be very interesting to do it. And the first question, we looked for any of the properties that are listed here. So finding an edge, a really clear edge, or finding a tail, finding knots also of star formation in the tail, finding asymmetric morphology, anything like that. So if you take a look at our paper on arXiv, there is at the end a huge appendix with all the images, and you can see more or less what they look like.
And you did research in single band images, or you made color images combining several bands?
Well, we didn't have several. For some, we had 2 bands. For many of them, we had only 1 band. And usually, if you make a color image, I think you need rather 3 bands. So we didn't really do that. So, but for those for which we had 2 colors, 2 bands at least, we could make the color magnitude. Well, this is the color magnitude diagram for Maxo 717. And for the other clusters, it was, I don't think we did this because there were few galaxies. I'm not sure it would have been, I don't have the equivalent plot for the other ones, for the other clusters, yeah.
Thank you.
Okay. Thank you, Valerie. Let's move on because there are many questions. So Gary, please.
Okay, thank you, Florence, for your nice talk. You're at the beginning of something big, I think. All right, I think it's very important to get these big samples of jellyfish galaxies, and they probably have diversity, so that's why we need big samples and understand them. Mm-hmm. Now, this said, there are many things you found that we expect, right? Because a jellyfish galaxy should be a RAM pressure strip galaxy. So to be a RAM pressure strip, you have a couple of requirements. You need to have gas, so they're not going to be passive. But you did find 1 passive galaxy. Maybe it's a passive galaxy with gas, obviously. So you need to have gas. You need to live in a cluster, and you need to have a high velocity in that cluster.
Yes.
And you need to have a low mass. Because
but they don't all have high velocities. If you look at your, some don't really have those that are here don't have a high velocity.
Well, though that's because you're looking in projection, but they might have a higher transverse velocity.
Sure.
Plane velocities.
Sure. Yes.
So I don't worry about that. And then they have to have low masses because if you work out a toy model of orbit averaged effect of RAM pressure stripping, you find that the effect goes as the ratio roughly of stellar mass to cluster mass to the power 2/3. So you want to be in a massive cluster and be at the same time a low mass galaxy. The reason why is that the lower the mass, then the less you retain the gas, right? So so that's one thing.
Yes,
ideally,
fact, if I may say something just before you move to maybe something else about the mass, there is There was a very nice paper by, I forgot the first author. The second is Annalisa Pilepic. In fact, she wrote to me after she saw my paper on arXiv, and she said, oh, maybe you'd be interested by our paper. And I don't know how I missed it, because it's really nice. It's numerical simulations of jellyfish galaxies in particular. And they also find that they have rather low masses. So it agrees with what you're saying.
Yeah, I should read maybe Donnarumma, I don't know. No. And then another thing is that have anyone done this with SDSS? You mentioned SDSS, because SDSS, the main galaxy sample of the SDSS has the advantage of being closer. So you have redshifts of 0.5, SDSS is typically 0.1. So you gain a factor in surface brightness, a factor of 4, which is 1.5 magnitudes. And since the stars that are removed are often in low surface brightness regions, not always, but that would help. So there might be selection effects with redshift.
Well, there have been a lot of work done on nearby clusters, like all the Poggianti work is very nice. Poggianti and Vulcani and I mean all her team. So they have been doing a lot of nice things about that. Yeah.
Now regarding the figures you showed, so it's very interesting. So I should sit down one day and make another figure where I plot the fraction rather than separating backsplash infall. I could simply plot those galaxies that have the fraction of galaxies that have high total velocities.
Okay. Yes.
And we can plot this in this projected phase space if you want.
Yes.
And,
yes, I hope that you can help me with this, because I also want to do the same kind of study for the next cluster that I'm working on now, and maybe there's something we could do together on the interpretation.
Okay, with pleasure. So I have to find where the data. This is based on simulations, obviously.
Yes.
And I've been throwing away a lot of simulation data on the pressure from the computer people, because they take too much disk space. But I think they still have it. Okay.
Yes. Well,
so okay. Did you look at that one galaxy that was very passive? Does it? Well, it'll be interesting to see its picture.
I'm not sure which one you're talking about.
There was in one of your diagrams. There was one galaxy which was completely more passive than all the other ones in one of the early figures.
Where is it?
Even there, you saw it in that scatter plot.
The one up here. This one.
Yeah, show me in specific star formation rates or SFR versus mass. Oh. A scatter plot. Yeah, so for example, the
two up here.
Well, no, those are very star forming. So you want to take the one on the lower,
the one down, right. Down here.
Yeah, that one is very passive. It'd be interesting to look at its morphology so, and understand, you know, so it had gas, but why did it have gas and not form stars, right?
I don't know. Yeah, I'll have to look at it. I don't know which one it is. I didn't check, but that's a good idea. It's easy to check.
But I'm sure you'll find many interesting things. You know, are the galaxies more concentrated or less concentrated given their mass? The jellyfish ones? I don't know. There are many things you can do. Are there internal velocities? You can do that one day. Different.
Yes.
Their metallicities. No, but who knows?
Okay, Gary, have you finished?
I am finished.
Okay, thanks very much. So let's move on. Nick Kaiser, Nick, please.
Hi, very nice talk, thank you. I had a simple question about the Cormandy relation. So are those values being corrected into the rest frame or those observer frame?
Those are observer frame.
Because it would presumably tighten up, right?
You mean applying the dimming correction?
Yeah.
Yeah, we tried, and then it messed everything up, and we were not sure we had to do this, so we finally ended up by just showing our data.
But it looks like it would tighten it up. You're saying it goes the wrong way?
Yes, I think so.
Interesting.
Maybe Aline is here and she can comment. Aline, you're here. I saw your name before. Are you
I
mute?
think she's gone for lunch. No, she's not.
She's not here anymore. Okay.
Here, given effective radius, given effective radius, your surface brightnesses are lower for the high redshift. So if you correct, it will go up. It will go in the right direction, but by how much, I don't know.
Yeah, but I think it's 1 plus z to the 4th power, and so it's a huge correction.
Yeah. So
you have a color term as well, a K correction.
Yes,
yeah.
but
which I can't do in my head anymore.
No, I don't know. I remember that Aline tried, and it ended up looking very strange. So we thought we'll just show our results, and then they can.
Because it's roughly in the right ballpark. You see, at redshift 1, we know that it's 10 log 1 plus z. So at redshift 1, you take 10 log 2, that's 3 magnitudes. And indeed, if you push the blue points up by 3 magnitudes, they fall in more or less on the lines.
I think the correction is really too high.
It might go too far. Yeah. But then, as Nick said, there might be a K correction.
Color, yes, maybe a color. So I'm sorry, I don't really have a good answer for this.
Nick, you don't have any further question?
Well, just one. I mean, in the ones the candidates you're finding in the Infor region, I mean, are they in groups? Do you look at do you have information on the local environment?
Well, all these belong to the MAXO 717 structure. So we don't really have detailed information on the presence of groups, but there's a main cluster, and then there is a sort of first filament, but very broad, that is like a second cluster that is merging with the first one, and then there is an extended filament that goes to the south, and altogether this structure is about, I think, 9 megaparsecs long.
Yeah, it's huge.
So it's one of the biggest structures that we detected with in a density map of red sequence galaxies. So now that I made this plot, in fact, I made this plot after I finished the paper, so I haven't done very much since, but I would like to see where they are located. I mean, the Infor galaxies and the backsplash galaxies, where they are located in the image that I showed in this large image here, to see which ones they are, if I can detect anything particular. Yeah.
Okay, thank you.
You're welcome.
Thank you, Nick. So Hakim, please. Hakim?
Yes, sorry, I was on mute. Yes, since we're talking about the star formation rate and the mass compared to the main sequence with the passive galaxies, so I guess this star formation rate comes from SED fitting, right?
Yes.
And for instance, MAX 0717, the redshifts, I guess they come from Muse data?
No, the redshifts were measured before that.
Okay, because with Muse out, I bet you can get star formation rate from H beta or something like that and compare.
I don't think there is Muse data for MAX 0717, or at least not covering the entire structure, because the Muse field is very small.
It's in the center. Yes, it's in the center. It's true. Yes.
So
yeah, I was just wondering if you can get better star formation rates for some of these jellyfish galaxies and compare with the SED fitting, because sometimes it can give you really wrong values.
You see, these are the SED fittings that we get. I mean, to me, I'm not a specialist, but they look nice.
Yeah, they do. For instance, for the O3 thing, I don't know why the flux is not boosted by the emission lines in the broadband.
Well, I don't know. I mean, it's probably just because it's just a small line in a broad filter, so it doesn't.
Yeah,
it's not sufficient to boost the whole flux in the filter.
Yeah, I was just wondering if you have other information.
But I'm rather happy with the SED fittings.
Yeah, it looks nice. Yes. And so my question was for the classification. You know, if you look at all the properties you derived before, if you look at that as a function of the for J1, for J2, for J3 to see if it evolves, so it's very different, so you can assess the contamination of your sample.
Yeah, that's a good idea. I didn't do that. Well, the problem is that J=1, we're not really not sure they can be jellyfish, but yes, it's a good idea to see if we find different, I mean, just making this kind of plot with different colors, for example,
yeah.
for different J's. Yeah, I'll do that. That's a good idea. Thank you.
You're welcome.
Okay, I don't see more questions, but thanks very much, Florence, for this very, very nice talk. Thank you.
Thank you.
So next we have got, at the same time, on Thursday, we have got Nathan Seacrest from Naval Observatory, US. And he's getting up at 5 o'clock in the morning to tell us all about AGMs and galaxies. So please join us. Thanks very much. Thanks, everyone. And thanks, Florence. Thanks very much.
Bye-bye.
Bye.